Sup nerds. So today I want to talk about modeling and logistic equation and how we could use first order ODEs to model certain phenomenon. So these are pretty useful applications. You could use them to calculate populations, maybe population growth or decline. You could talk about the spread of stuff that goes viral like a rumor or disease, or you could use it to calculate interest rates for maybe loans or savings accounts, or concentrations of salt and other liquids. Most of the time, the hardest part of creating these models is setting up the differential equation. So you'll see with a lot of these upcoming examples that setting up the differential equation is the tricky part, and then solving it's not too bad, and we could actually do a lot of different models based off of just the few techniques that we've learned with solving separable and or linear first order ODEs. So let's jump into a salt example. So this example can be adapted to different types of mixtures that you might see in chemistry or in nature. So here we have a tank full of water. It's not pure water though, it's 100 liters of salt water, and the salt has a concentration of 1 gram per liter. Okay, and we're gonna pour pure water in here, and then a well-mixed mixture is going to pour out at the same rate. Okay, so pure water is coming in, but salt water is leaving. So we're sort of diluting this tank. And we're pouring water in at a rate of 2 liters per minute, and the mixture is leaving at the same rate, 2 liters per minute. So it could be useful to solve for an equation telling you what the concentration is at any time or what the salt is at any time. So that, say you're cleaning a tank, you want to know at what point you reach a certain level of purity, or at what point is your reservoir a certain level of cleanliness. So the issue is it's hard to solve for a certain level of concentration because concentrations don't add well. If you take a cup of salt water, where it's 50% salt, 50% water, and add it to 2 cups of pure water, then you can't really add the concentrations. You know you're going to have 3 cups, and half of a cup is going to be salt. So only 1/6 of the solution is salt, but you can't just add 50% plus 0% to get 1/6. So concentrations aren't the right quantity to work with because of this issue. So we're going to set up our differential equation using mass, so like the amount of salt in the tank at any given time. Let's call this quantity S of t, and we can't find S of t directly. We need to set up a differential equation where S prime of t is the amount of change in salt in the tank. So the total amount of change is equal to the amount of salt that's entering minus the amount of salt that's leaving. Now that's pretty intuitive, but setting that up mathematically is usually the most difficult part of these problems. So the amount of salt entering in this case is 0 because we're pouring in pure water. Now the amount of salt that's leaving is a little bit trickier. You might be tempted to say, oh, there's 100 grams of salt in the tank, it should be 100 grams times 2 liters per minute divided by 100 liters. That would be the concentration times the rate at which it's leaving. But the issue is the concentration is changing. It's not just 100 grams per liter the whole time. As time goes on, it's going to be getting diluted. So we actually need to put an S of t in here. And so S of t over 100 is the concentration at time t, and then multiply that by the rate at which it's leaving. So this gives us our differential equation. Now, I highly suggest you pause and think about why this is the way the differential equation should be set up and how the changing salt changes the amount of salt is leaving at time t. So once you have the differential equation set up, it's not too bad to solve. It's just S prime equals S over 50. And so this is a linear first order ordinary differential equation. We just multiply by our integrating factor e to the t over 50. And then integrate both sides. And we should just get S of t times our integrating factor is equal to some constant. And so S of t is equal to some constant times e to the negative t over 50. And we could easily solve for the constant by plugging in our initial conditions. We have 1 gram per liter times 100 liters is our initial amount of salt. So S of 0 is 100 grams. So we found an equation for the amount of salt at time t. It's 100 e to the negative t over 50. So as a good sanity check, and you should do these with all these modeling problems, you should maybe plug in certain values and maybe think about when time goes to infinity. In this case, as time goes on to infinity, the salt goes to 0, and that checks out with what this problem is saying. It's like if we're just pouring in pure water, then as time goes on, it's going to get more and more diluted, and there's going to be less and less salt, and the salt is going to go to 0. So it checks out. As always, you should pause the video and rewind if there are any parts that were unclear. If you're unsure about, you should definitely work out these examples on your own, filling in any details you're unclear about. Now let's do a few other examples that are similar to the one we just did. There'll be different iterations. Now for the second example, we'll flip the problem on its head, and instead of pouring pure water into a salt water mixture, we're going to pour salt water into a pure water mixture. So we're going to start with a 120 liter tank of pure water, and the salt water mixture that we mix in is going to have 5 grams per liter, and it's going to enter at a rate of 2 liters per minute. And then we're going to let the mixed water from the tank leave at a rate of 2 liters per minute. When we set up the differential equation, now S prime of t is equal to the amount of salt in minus the amount of salt out. So the amount of salt entering isn't too bad to calculate. It's 5 grams per liter times 2 liters per minute. Okay, so that's straightforward. And then the amount leaving is similar, where it's the concentration at the time t, which is S of t over 120 times the rate at which the solution leaves, so 2 liters per minute. So definitely pause and think about why the differential equation is set up like this before we go in to solve it. And hopefully once you understand this, the solution is really straightforward, and I trust that you all can fill in the details. I'll go through it pretty quickly, and you're welcome to watch in slower time if you want to fill in the details alongside, but it's the same idea of finding the integrating factor and solving a first order linear differential equation. Once we're done solving for the ODE, we end up getting S of t is equal to 600 minus 600 e to the negative t over 60. Now, as time goes to infinity, the salt goes to 600, and this is a good sanity check. The salt should be going to 600 grams because, well, we have 5 grams per liter of salt entering, and then we have 120 liters. So as time goes on, the mixture in our tank is going to have the same concentration as the water that's entering. The salt water that's entering has 5 grams per liter, so the tank should end up, as time goes to infinity, with 5 grams per liter. So this is a good sanity check, which you should always do. So our third example is going to be a hybrid of the previous two examples. This time we're going to have a saltwater concentration in the tank and a saltwater concentration entering the tank, but they're going to have different concentration. So we're going to have 120 liters of water in the tank, and its concentration is going to be 3 grams per liter. And we're going to have water entering at a rate of 2 liters per minute, and the entering water is going to have a concentration of 5 grams of salt per liter. And again, the mixture is going to leave at the same rate of 2 liters per minute, so the total volume is staying constant. This time our differential equation looks exactly like the same differential equation as equation 2, because the initial conditions don't affect the differential equation. They will just change the value of any unknowns at the end. So we set it up the same way. The amount of salt coming in is still going to be 10 grams per minute, and the amount of salt leaving is still going to be whatever the concentration is times 2 liters per minute. And so we get the same general solution as the previous one, 600 plus c e to the negative t over 60, but we get a different starting value. So this time our c is negative 240. But again, as time goes to infinity, our salt should be going towards 600. So one last variation of these types of problems, we might have a tank that starts with certain volume and concentration, say 100 liters of water with 3 grams of salt per liter. And we might have a salt water mixture entering, say, like 4 grams per liter of salt, entering at a rate of 10 liters per minute. But this time we'll have the mixture leaving at a different rate than the rate at which it enters. So say 10 liters per minute are entering, but only 5 liters per minute are leaving. So this changes things a little bit. So the amount of salt entering is still going to be, well, the concentration of the salt water mixture coming in times the rate at which it comes in. But the salt leaving is slightly different because the concentration is, well, we have to factor in the volume. So now the concentration is S of t over 100 plus 5t. Okay, so 100 plus 5t is the volume at time t. Now I highly suggest pausing and thinking about why this is the volume and why this is the concentration of salt at time t. So once you think about that and realize that's the concentration, and then the rate at which the mixed solution is leaving is 5 liters per minute, then this gives us this differential equation. So it's a slightly harder differential equation than what we had before, and we have initial conditions, of course. S of 0 equals 300 grams, but this gives us, we could still solve this. It's still just a first order linear ODE, so our integrating factor might look a little more complicated than the previous examples, but in this case it actually simplifies nicely, and you could go through the solution slowly if you want. So after working through the solution, you should still do a sanity check. So in this case, S of t, we have an expression for it. It's 4000t plus 100t squared plus some constant, which turns out to be 30,000, all over 100 plus 5t. And if we take S of t and divide it by 100 plus 5t, that'll give us the concentration of the solution, and this should go towards the concentration of the incoming water. So if you take the limit as t goes to infinity, it checks out and you get exactly 4 grams per liter. So the last thing I wanted to talk about today is population models. And of course we have exponential growth where y prime is equal to some constant times y. So this would be an example where a population grows as twice the rate of what the current population is, something we see with uncontrolled populations. And these are easy to solve. It's just y equals the initial amount, so a times e to the kt. A more interesting example is the logistic equation, where y prime equals some positive constant k times m minus y times y. M can be seen as a carrying capacity. It's like a limit for the function. So this is more common than the exponential growth that we would see. And so to see this, if y is between 0 and m, then the population is below the carrying capacity and our derivative is increasing, so the population would be growing. And if y is bigger than m, then just working out the signs of each term, then y prime would be negative and it would be overpopulated, leading to too much competition, the population would decline. So the phase diagram for this solution would look sort of like a bunch of curves converging towards m. We'll only consider positive y because negative populations don't make sense. Now we looked at a solution of the logistic equation. It's not too hard to solve. It's just separation of variables. We'll have to use partial fraction decomposition. After you solve the logistic equation, you could still do a sanity check where you let t go to infinity. And when you take that limit, you notice that the population y of t goes to m. So this is a good check that we're on the right track. So again, go through any of the parts slower if you need to review some of the solutions. And if you enjoyed the video, smash the like button and subscribe. And if you have any questions, drop them in the comments. Till next time.